Hi everyone, welcome back to my channel Maths with Math Tips. This is the second lecture series of WBSET 2020 Mathematical Science. This is question booklet series X. Those who are new in my channel, the first video is not watching, so please I share the link of this first video in the description and also here in the I tab. So please go and check this video. Now we start this video, and before starting this video I am requesting you to all those who are new in my channel, please like the video, comment if you have any doubt in the comment section below, and subscribe the channel. So let's start. Question number 10. Question number 10 says that let xn be a sequence of real numbers, then limit n tends to infinity xn exists even or if the fourth option is given here. Now we know that if limit n tends to infinity xn exists, that means this sequence is a convergent sequence. Now if the mother sequence xn converges, then we know that all its subsequents are convergent. So limit of all its subsequents exist, but not conversely. That is, if the limit of subsequents exists, then this does not imply that limit of the mother sequence xn exists. Now option A says that limit n tends to infinity x to n and x to n minus 1 exist. Now here we take an example xn equal to minus 1 to the power n. We know that this sequence is not a convergent sequence, but the subsequence x to n equal to minus 1 to the power 2n, and this gives 1 always, and this is a convergent sequence and which converges to 1s. And if we take x to n minus 1, that is minus 1 to the power 2n minus 1 always odd. If we put the value of n, then 2n minus 1 is always n, which is equal to 1 minus 1 always, which is also a convergent sequence. But the mother sequence xn is not convergent, so we discard this option. Similarly, by same example we can discard option number B, and similarly by taking this option we can also discard option number D. So here clearly option number C is correct here. Also, to check option number C, here we use a result. The result says that if three subsequences x3n, x3n plus 1 and x3n plus 2 converge, that is limit exists, convert, then the main sequence xn is also converge. If we use here this result, then we can also say that option C is true here. Now we go to the next question, question number 11. Question number 11 says that let f from closed interval 0,1 to 0,1 be a continuous function and fnx equal to x to the power n for all n. Therefore, it is clear that fxn, since fx belongs to open interval 0,1, so fnx must tends to 0 as n tends to infinity. This is clear. Now here we use the Dini's theorem. That means the limit function fx is equal to 0 for fxn for this condition. Now by Dini's theorem states that if fnx is a continuous function, continuous and monotonic, that is monotone, increasing or decreasing, then the sequence of functions converging to a continuous functions fx, here fx is continuous given, converging to fx on a closed interval, here given that the interval is closed interval 0,1, then the convergence of fnx is uniform, that is fnx converges to fx uniformly. Convergence of fnx is uniform. So by Dini's theorem we can directly say that the fnx is converges to f uniformly. So B option is correct here, and B true implies A is false here. Also, here a result says that suppose fnx be a sequence of function bounded, which is bounded on closed interval AB. Fnx be a sequence of function which is bounded on closed interval AB. Here the closed interval AB given, that is 0, 1, and fnx converges to fx uniformly. These two gives a result limit n tends to infinity integration a to b fnx dx is equal to integration a to b limit fnx dx. This result, and we know that this limit function is fx, so this is equal to integration a to b fx dx, and the value of fx is 0 here, so we put this value. This is equal to integration a to b 0 dx, and which is equal to 0. So this gives the value of this limit is equal to 0. So this is wrong option and this is correct option. So we go to the next question, question number 12. This is directly based on result. So the question says that consider the following statement: every monotonic function on closed interval AB is of bounded variation on AB. This is direct result questions, so this is correct statement, so S1 is correct. And S2 says that every continuous functions on AB is of bounded variation on AB. Here bounded variation, continuity does not imply bounded variation, because we have also condition which is bounded derivative. Continuity plus, this is a theorem also, bounded derivative. We have also bounded derivative for this function on open interval AB. We need these conditions for S2 to be true, so this is not correct. And every function of bounded variation on AB is absolutely continuous. This is also direct result. This is not correct option. And every absolutely continuous function is of bounded variation. This is direct results question. So S1 and S4 are correct. These two are direct to theorems. So S1 and S4 is correct. That means option C is correct here. S1 and S4. Now we go to the next question, and before go to the next question, how about the video? If the video is helpful for you, then please give a like to this video. Question number 13. Now question number 13 says that if E subset of R is uncountable, then which of the statements is true from these four options? Now since E is uncountable and E is a subset of R, then we can take E as set of rational number. This we know that this rational number subset of real number, correct, and the limit points of QC is also R. Limit points of QC is equal to R. So which is uncountable, so it is directly says that he has uncountably many limit points. So option C is correct here. Now option question number 14. Question number 14 says that if A from minus A to a difference 0 to open interval 0 infinity satisfies this limit is equal to 2. Now the value of this we can break it, limit x tends to 0 fx plus limit x tends to 0 1 by fx is equal to 2. Now here the 0 is out of the interval, so we can write 1 by fx also. Now this value is given here, so the limit of these two functions must exist. Let us take limit x tends to 0 fx is equal to suppose L. Then since fx not equal to 0, therefore limit x tends to 0 1 by fx, this is equal to limit this is equal to, we can write 1 by limit x tends to 0 1 by limit x tends to 0 of fx. So this is equal to 1 by L. Now this value is given 2 here. Therefore we write L plus 1 by L is equal to 2 from this condition. Now we simply find the value of L. So this implies L square plus 1 by L is equal to 2. So this implies L square plus 1 equal to 12. This implies L square minus 12 plus 1 equal to 0. This implies L minus 1 whole square equal to 0, and this gives the value of L is equal to 1 and 1. So the limit of fx is equal to 1. So directly option B is correct here, and A and C are incorrect options. Now we go to the question number 15. Here we use a concept. The question number 15 says that if f is a real valued function which continuous on R satisfies this condition, and f0 equal to 1, f dash 0 equal to 2, then find the value of f2. Here we consider the function directly by use these conditions and these two conditions, and this is the combination of linear functions. The linear functions, what is the linear function? Linear functions such that f of x plus y equal to f of x plus f of y, and condition number 2, if any function satisfies these two conditions, then we say that this fx is a linear function. Now if we note this condition, then this condition is mixed of these two conditions, so we must say that f is a linear function. So we can take fx equal to ax plus b, which is a linear function. Also you can take direct the value of ab. Suppose if we take fx equal to 2x plus 1, then say that this f0 equal to 1 satisfied, f dash 0 equal to 2, f dash equal to 2, which is f dash 0 equal to 2, which is also satisfied, and this conditions is also satisfies. Let us check it. Suppose let us check ax plus b. This is the particular case. So f of x fx equal to ax plus b. Therefore fy equal to ay plus b. Ax plus b plus fy means ay plus b by 2. So this is equal to 2 into 2a, sorry, this is equal to a common x plus y plus 2b by, right, 2. F of x plus y by 2, I have to find this value. So f of x plus y by 2, this is equal to a into x plus y by 2 plus b. This is the value, and we have note that this is equal to this. So ax plus b is satisfied also this condition, x plus y by 2. And if we find then value of a and b, then we simply put this and this to get the value of a and b, and we note that the value of a is 2 here and b is 1 here. From these two conditions I can directly take this function fx equal to 2x plus 1. Therefore the value of f2 is equal to 2 into 2 plus 1, which is equal to 5. So option C is true here. Question number 15. Now we go to the next question, question number 16. For what value of k the functions fxy equal to sine inverse x plus xy minus 2 by tan inverse 3xy minus 6, and at xy not equal to 1 2, k equal to xy equal to 1 2, continuous at 1 2. So to prove the continuity of these two variable function, take y fixed. So keeping y fixed, we first find the value at x tends to 1. So limit x tends to 1, f of xy is equal to limit x tends to 1, f of xy means sine inverse xy minus 2 by tan inverse 3xy minus 6, this. Now if we put the value of x equal to 1 here, then this is 0 by 0, so we apply L'Hospital rule, keeping y fixed with respect to x, with derivative these two functions with respect to x. Therefore limit x tends to 1, sin inverse x means 1 by root under 1 minus xy minus 2 whole square, and if we take derivative of this function xy minus 2 with respect to x, then we get value here y. So and tan inverse x means 1 by 1 plus 3xy plus minus 6 whole square, and if we derivative these functions, then we get here 3y simply. So now we put the value at x equal to 1, which gives y by 1 root under 1 minus gives y minus 2 square, this is square, and this gives 3y by 1 plus 3y minus 6 whole square. This. Now we take limit as y tends to 2. Now taking limit y tends to 2, since x and y goes to 1 and 2, we get this is equal to, this function is equal to 2 by root under 1 minus 0 by 3 into 2 means 6 by 1 plus this gives 0. So this is equal to 2 by 6 directly, and this is 1 by 3. Now 1 by 3, so the value of this limit is equal to 1 by 3, and if we take the functional value for continuity of f at 1 2, this the value of k also gives 1 by 3, so 1 by 3, yes. So option B is directly correct here. Now we go to the question number 17 and 18. Question number 17 says that x cube log y by x is a homogeneous functions of xy of degree. Now the definition of homogeneous function is says that f of lambda x and lambda y is equal to lambda to the power k fxy, then this function is called homogeneous functions of degree this k, where lambda greater than 0. Now fx equal to here given fxy equal to x cube log y by x. Now we put f of lambda x lambda y, also the variable may be 2 or 3 or 4 or maybe. Now f of lambda x lambda y, this is equal to lambda x whole cube log of lambda y by lambda x. Lambda cancel, so this gives lambda cube into x cube log of y by x. So this is equal to lambda cube into f of xy. So this gives k equal to 3 here. Therefore the homogeneous functions is of degree 3 here. So D is the correct option here. So if the video is helpful for you, then please give a like to this video and comment if you have any doubt in the comment section below. Now we go to the question number 18. Question number 18 says that the degree of splitting field fx equal to x to the power 4 minus 2 over q, the set of rationals is. Now let us suppose that let k be the splitting field. K be the splitting field. Now first we find the roots of this equation fx. So roots are fx equal to 0. This gives x to the power 4 minus 2 is equal to 0, which gives the roots are x equal to plus minus 2 to the power 1 by 4 and plus minus 2 to the power 1 by 4 and iota. These 4 are the roots of this equation x to the power 4 minus 2 is equal to 0. Since k is a splitting field, so since the splitting field k of x to the power 4 minus 2 over q, it is the field generated by all the roots of the polynomial. Now we see that k equal to q of 2 to the power 1 by 4, 2 to the power 1 by 4 iota minus 2 to the power 1 by 4 and minus 2 to the power 1 by 4 iota. This, but the roots minus 2 to the power 1 by 4 and minus 2 to the power 1 by 4 iota are redundant. Therefore k equal to q of alpha iota alpha. This is equal to, you can write q of alpha and iota, this. Now since q is a splitting field, we can write as this equal to q of these roots. Suppose I take the roots as alpha, so we can write this alpha I q alpha over q, and that is where alpha is the roots. Alphas are the roots of these four roots, alphas. So now degree of this alpha over q, it is 4, and because alpha is a root of the irreducible polynomial x to the power 4 minus 2, so degree of this is equal to 4, and degree of alpha I over q alpha is equal to 2. So this gives 2 into 4, which is equal to 8. This is the correct answer here. So the degree of this splitting field is equal to 8 here. Now we go to the question number 19. Here question number 19, I use a diagram here. This is field, this is Euclidean, this is P, that means prime principal ideal ring, PID, this means PID, P means PID, this means U means unique factorization domain, and this means ID, integral domain. Now field implies this all. Field implies all E, PID, PID, and so on. UFD, unique factorization domain, ID, and so on. And ED implies this for rest, PID implies this to rest, UD implies this to rest. Therefore, every field is integral domain, principal ideal domain, unique factorization domain, and integral domain. And here given that every Euclidean domain is unique factorization domain. Every Euclidean domain, Euclidean domain means principal ideal domain and unique factorization. So this is correct statement, and here we have to find the not true option. So it is correct option, it is not true. No? This is true option. Every unique factorization domain is an Euclidean domain. It is noted that Euclidean domain implies unique factorization domain, but not conversely. Unique factorization domain does not imply Euclidean domain. So this is wrong option. For this option, this is not true. 19, option B. Now every integral domain can be embedded in a field. This is correct option. So this is not true, not correct. and ring of polynomial fx where f is a field is also principal ideal element. This is also correct statement, so this is not wrong option. So option B is correct here from this concept. Now I skip question number 20 in this video. Now question number 21 says that let fp denote the field z upon pz where p is a prime and z is a set of integers. Let fp x be associated with polynomial ring, then which of the following rings are filled? We simply check that this polynomial is irreducible over f5x. If we find that this is irreducible over this, then we clearly say that this is a field. Now the elements of f5 are 0, 1, 2, 3 and 4. Now we check this gives 0 over f5x or not. So x square plus x plus 1 at x equal to 0, this gives fx gives, suppose this is fx, fx equal to 0 means, and this is modulo, suppose modulo 5. 0 means modulo 5, modulo 2 and modulo 3, modulo 2, modulo 3. So this x equal to 0 means this is 1, and modulo 5 means this is 1, modulo 2 means 1, modulo 3 means 1. X equal to 1 gives x cube, oh sorry, the polynomials are also distinct here. So if I find this, first find x cube plus 1, x square plus 1. Okay, no problem here. So x equal to 1, this gives 3, modulo 5 gives 3, modulo 2 gives 1, modulo 3 gives 0 here. So this is not, so here f5 we cannot take this. We check whether modulo 5 0 or not. If here we get 0, then this is reducible over f5x. If get 0 here, then it is reducible over this. But if we don't get any 0, that is non-zero, then it is irreducible over f5 or f2 modulo 3. So x equal to 2 gives, this gives 4, 6, 7. Modulo 5 gives 2, modulo 2 gives 1, modulo 3 gives 1. X equal to 3, this polynomial gives, this is also only for mod 5. X equal to 3 gives 9 plus 3, 12, 13. 13, which is modulo 3, non-zero. X equal to 4, also non-zero. 4 means 16, 21, which is modulo 5, non-zero. So this is irreducible over f, this is failed. Therefore now we check option 3 first. f3 over x cube plus x plus 1. X cube plus x plus 1 over f3. Over f3 we have to find. f3 means that the element of f3 are 0, 1 and 2. Therefore at x equal to 0, this polynomial gives 1, which is modulo 3 means modulo 3 gives 1. X equal to 1, this polynomial gives 3, which is modulo 3 gives 0. So this is reducible. So this is not filled. Therefore we discard the options where option 3 is given. So here it is given, so it is not filled. B option incorrect. Here also this is also incorrect. All of the above incorrect. So option 3 is clearly true. We don't need to check option 2. If you can check this, so you also find that this is irreducible over f2. So in this video, this is the last problem. So how was the video? If the video is helpful for you, then please give a like to this video, and if you have any doubt so please comment in the comment section below and subscribe the channel. So thank you friends.